Welcome back to Protovenix Verilog Masterclass. Before we start writing Verilog code, let's first understand the bigger picture, how digital design works and why Verilog became so important in the world of hardware engineering. Digital design with Verilog HDL is a crucial aspect of modern hardware engineering, allowing engineers to model, simulate, and synthesize digital systems ranging from basic logic gates to complex microprocessors. It offers a way to describe the structure, behavior, and timing of electronic circuits in a textual format, which is fundamental to today's technology. Digital design started decades ago with manual wiring and paper schematics. Then came schematic-based CAD tools. They made logic gate design faster, but still complex for large systems. This early evolution, from manual methods to computer-aided design, laid the groundwork for more sophisticated approaches. That's when hardware description languages, or HDLs, changed everything, providing a more efficient and scalable way to design circuits. CAD tools evolved to automate the design process, from drawing circuits to describing them using text-based models. This transformation began in the 1960s with innovations like Ivan Sutherland's Sketchpad, which allowed graphical interaction with computers. Designers could now simulate, synthesize, and verify circuits before even fabricating them, significantly reducing development time and costs. Modern CAD tools integrate AI and machine learning for generative design and cloud technologies for connected production systems. Two major languages shaped this revolution, Verilog and VHDL. They allowed engineers to describe circuits using behavioral, data flow, or structural modeling, making digital design more modular, scalable, and reusable. Verilog's syntax resembles C, making it easier for those with a C background, while VHDL has a more verbose syntax inspired by the. Both languages enable engineers to simulate circuit responses before fabrication, ensuring functionality and performance. Here's the typical HDL design flow. First, write Verilog code to describe your logic, which is known as design entry. Next, simulate the design to verify its behavior and ensure it meets specifications. Then, synthesize it into a gate-level representation, converting the high-level description into physical gates. After that, implement it onto an FPGA or ASIC, mapping the design to the target hardware. Finally, test the real hardware output to validate its functionality and performance in a real-world scenario. Now you might ask, why Verilog? Because it's simple to learn, widely supported by all major FPGA tools, and it mirrors C-like syntax, making it easier for programmers to adapt to hardware logic. Verilog is an industry standard, offering flexibility and supporting various levels of abstraction, from high-level behavioral descriptions to gate-level structural definitions. Its widespread adoption makes it a valuable skill for any aspiring hardware engineer. HDLs keep evolving. Today, we have advanced languages like System Verilog, Chisel, and BlueSpec, blending hardware and software concepts for modern chip design. System Verilog, a superset of Verilog, offers enhanced features for design verification, while Chisel, embedded in Scala, allows higher levels of abstraction. Verilog remains the foundation, and mastering it unlocks your future in VLSI and FPGA development, providing a strong base for understanding these advanced languages and methodologies. So that's your overview of digital design with Verilog HDL. We've covered its evolution, the role of CAD tools, the emergence of HDLs, the typical design flow, and why Verilog is so important. In the next video, we'll jump into coding, understanding the structure of a Verilog program and how modules bring logic to life, giving you the practical skills to start your journey in hardware design.